Welcome to Techstination. Joining us is David Michaud, Director of Central Processing at the National Weather Service. Thank you for joining us, David.
Yeah, it's good to be here. Thank you.
Well, the press release reads, the United States is reclaiming a global top spot in high-performance computing to support weather and climate forecasts. Some new supercomputers are on the way. I'll let you give us some of the information, some background.
Sure. We recently awarded a $5.2 million contract, 10-year contract here at the National Weather Service. And this contract is a replacement for follow-on, for the current contract that we have in place now. And with this contract, we'll actually be getting our computing provided to us through an integrator as a managed service. So what that means is we'll have the integrator providing us both two supercomputers, and they will also be responsible for the facilities that those reside in, and also the services. So we expect to get two new supercomputers. They'll reside in Manassas, Virginia, and Phoenix, Arizona, and they will be approximately 12.1 petaflops in size per system.
What does that mean in terms of the computing power in comparison to what you have today?
In comparison to what we have today, this will be an approximate 3 times increase in computing power. It'll be about a doubling of the network interconnect speed that connects all the different nodes on the system, and it'll also be a doubling of the storage capacity that we have today on our current systems.
And is it different than the way things are operated today because they're essentially being contracted with, or is that the way it's done now?
Currently, we have a contract, and we have our integrator doing a similar sort of thing where they provide the facilities and the systems. I think what's different with this contract and the systems that we have and the way they're being delivered really has a lot to do with the configuration of the systems that we have. Under our current contract, we actually have 4 separate compute clusters per site. So we divide our workload across those 4 different compute clusters. And under the new contract, we expect to have 1 system per site. So what that really means for us is that we can run, when we run our applications, we can run one execution for 1 application across a larger number of compute processors. So we're not really limited by these smaller segments of compute. We can actually run one larger execution. So that gives us more capability to do larger things with our applications on these systems.
Tell us a bit about the applications and what this you hope will mean for you in terms of results here.
Yeah, so we run a suite of models in real-time mode. So we have our models running anywhere from 4 times a day for certain types of models, for instance, our global forecast system. And we have other high-resolution, rapid refresh, kind of smaller scale models that run on an hourly basis. And what we hope to get or to do with the new supercomputing power is drive to a number of different things. One of those would be working towards higher resolution models. So what that really means is that we can predict weather events of smaller and smaller scales with higher resolution, so things like thunderstorms or flash floods. So that would be one aspect of improvement we'd be looking for. The second aspect would be to run more comprehensive models. So kind of you can think of it as increased complexity. So to more accurately capture the variety of weather phenomena that impact us, like when snow changes to rain, or the better use of observations to describe the state of the atmosphere. And the third piece would be around ensembling. So a larger ensemble of models that allow us to provide better information about how confident we should be in a particular forecast. So you can think of a weather ensemble as taking one of those weather models and slightly changing the conditions that the model begins with, or slightly changing how that model runs. And if you run a large number of those at the same time, you can look to see how those models either diverge or how they hang together in the solution. If they're close together in a solution, that gives us a greater idea that we'll have more certainty in the forecast. As those ensembles diverge, then that is an indicator that we should have less confidence in the forecast. So putting together all of those three aspects of how we would improve the models, that's how we would take advantage of these systems. So each of those improvements really require more computing power.
This is more serious than me deciding whether or not I need to bring an umbrella when I step outside the door today, because the weather affects so many things, including the economy in many ways.
Yes, absolutely. So as you point out, we can use these models for helping the public to make some basic decisions. Within the Weather Service here, we also use these forecasts as our input, or our way of working with decision makers in the community. So we work very closely with emergency managers, both at the local, the state, and the federal levels, to provide indications of what the impact of that weather event may be. And then this is very helpful to help these decision makers determine how communities should best react to that weather phenomenon that's coming. So, for instance, evacuations for hurricanes, or warning people of impending extreme weather events like flooding, and how to best deal with that in the community. So that's another aspect. And then, as you mentioned, with the economy, there's certainly a lot that can be done with weather information. So you can think of
agriculture, things like that.
Yeah, agriculture. So what types of seed you should be using? Certainly, there's aspects of insurance and reinsurance, and then there's you can also think about risk information. So if you're, for instance, a candy company, for instance, and how much cocoa you should buy in advance from a futures perspective, that can be a multi-million-dollar decision for certain corporations to figure out how to navigate that decision. And weather is certainly it's a highly sensitive aspect of their decision-making process.
And the new system will come online not for a little more than a year then, or when can we expect to see this?
Yeah, correct. It'll be in a little bit. So our current schedule is to have the delivery of these systems. So our integrator will order these systems. They'll be delivered. They have to be installed and configured, and then we go into an acceptance testing. That'll take about a year. So we expect all that to be complete by February of 2021. And then once that's complete, it takes us about a year to do all of the code migration of our current production suite from our current systems to the new systems, to do all the testing and the code checkout that's necessary to ensure the integrity of the modeling suite. And that takes about a year. So we expect to go live with these systems in operations in about 2 years, in February of 2022.
And these are two new Cray computers. Is this system kind of in competition with the kind of thing that IBM is always talking about?
Of course there are multiple providers out there. This would be a Cray Shasta system. So this system would be about 12 petaflops. It would be featuring an AMD EPYC Rome processor. So each processor would be has a 64-core processor at about 2.25 gigahertz, and within each system, they'll have about around 330,000 cores per system, and about 1.3 petabytes of memory within each system. So that, yeah, these are fairly sizable systems. And as you mentioned, there are various providers that are out there that provide both kind of CPU-based systems, systems that are CPU-based and accelerator kind of hybrid systems, and others that are pure kind of accelerator types of systems. So for our mix, we would expect to have just a pure CPU-based system like an x86 based system.
330,000 cores?
Yeah, that's correct. That's correct. Can do a lot of calculations. I think about this often, and you try to put that in terms that would be somewhat that you could comprehend. So if you look across both of our systems, that's well over 650,000 cores between the two systems. That's about 24 quadrillion calculations per second that this system can do. So, one interesting way I look at it is if you look at the population on Earth, if you think about your math teacher, everybody gets math homework, right? So let's just imagine everyone gets a math homework with 100 math questions like we did in grade school. So if everyone did their math homework every night, and everyone on Earth did that at the same time every night, our computers could do about 85 years worth of everyone's homework in the world in about 1 second. So it's pretty amazing when you start to kind of wrap your head around how quick these systems are. And on the storage side, that's equally as mind-blowing for me. We'll have about 26 petabytes of usable space per system. That's about 50 petabytes of usable space between both systems. So if you look at the total written works of mankind from the beginning of recorded history in all languages, that's reported to be about 50 petabytes, and that's what our system can store. For the others out there that like social media, that's about 350 billion Facebook photos that could be stored on these. Or for those that just like paper, it's about it can store about 1 billion 4-drawer filing cabinets full of text. So just pretty amazing stuff.
Hard to get your head around. So is it going to improve the long range forecasting? Will we be able to see farther out? Or is it really looking at the same kind of range you have now, just doing it better? So currently our global forecast models forecast out to about 16 days. And a lot of those aspects that I described earlier with higher resolution and kind of more complexity and dealing with the uncertainty of the models, certainly there's focus on those sorts of things. And then getting out to weeks 3 and 4 in terms of skill and with the models is something more that we're driving towards as well. So not just out to a day or two, but certainly out to the week 3 to 4 time frame is in our interest. And you're not just looking at the United States. You've mentioned several times global forecasting.
That is correct. Yeah. So if you think of how these weather models might fit together, if you look at a global model, it's certainly ideal to have the whole continuum of weather across the globe. And you can just imagine all of that weather flowing across the globe. And as you mentioned, the weather doesn't stop at the West Coast or the East Coast. So we're interested about, what weather is coming into the domains of interest that we have. And then those feed into these smaller scale models. So they'll feed into the boundaries of these smaller scale models, which we do run at these more limited geographical areas. And so you have to have that global model to feed into these smaller scale models to understand kind of what's coming in and out of these domains. Within the Weather Service, we do have forecast areas with our Aviation Weather Center and also our Ocean Prediction Center that do cover the entirety of the Atlantic and Pacific Ocean. So the domain that we have, even from just a forecast basis outside of the models we have, is pretty massive.
And is data shared internationally between your work and what goes on in other countries as well?
Yeah, internationally, it's both the modeling data that we share. So we do have a set of ensembles that we produce where we incorporate both our global forecast models and, as I mentioned, when you increase the membership of ensembles, that'll help to increase the accuracy of these systems. So we incorporate other global models into these ensembles, and we try to coordinate how those are configured so we can get a larger ensemble of information. So that's one example of sharing the model predictions and the guidance that's produced out of the supercomputers. But another important aspect as well is sharing the observational information. So we do internationally all share that weather information, and that helps to define the starting point of these forecasts. So the better we can assimilate that data into our systems and understand that starting point of the model, that's going to also help with the accuracy of the model. And it's very important to have all of that data on a global perspective.
And you've touched on it somewhat, but I don't know if you want to wrap up telling us the importance of this. There's a lot of concern, obviously, everywhere about weather today.
Yes, absolutely. So, to wrap up, I would say that getting to more accurate weather information is certainly very important to us, and we're very excited to be able to incorporate the masses of all the observational data that I mentioned from around the world and new observational systems that will be coming online into the future. That's going to help us with the accuracy and increasing also the skill of the forecast. And once we have the increased accuracy, or as we increase the accuracy of the forecast, that's really important for us to give the best possible information that we can to the decision makers in the community, which will help to relay the impact to all of us that are living in these various communities, so that we know what to do when weather is approaching. And I think that's really what's most important with these supercomputers, is to get the best information so that combined with better preparedness across these communities, once we see things happening, we know what to do and we can keep America safe.
David Michaud, thank you so much for taking the time with us.
Thank you very much. It was a pleasure.
Now this. How many companies out there have continued to innovate when it comes to building a better radio? I'm Fred Fishkin, host of Techstination, and I'm here to tell you about the new CC Skywave SSB radio from the wonderful people at C. Crane. Bob and his crew really love radio, and it shows in this new compact model that is packed with features. Beyond great AM and FM reception and sound, you can tune into shortwave signals from around the world, Listen to ham radio operators, aviation, and more. It's the radio you'll turn to every day and in emergencies. It will run for nearly 3 days on just 2 AA batteries. Pair the sleep timer with the new Soft Speaker 3, and you've got the perfect radio for your nightstand. Of course, it can wake you up too. Click on Crane at Techstination.com and put in the code Techstination for a free flashlight with your order. They love radio, and you'll love Crane.